Well, hello everyone and welcome back to Adrian's Digital Basement. First off, a little housekeeping. I want to point out something that I do on a lot of my videos that people may not be aware of. When I have long videos with lots of different sections in them, to make it easier for people to jump right to the part that they're interested in, I always put in the description some links that jump directly to those sections. That way, if you've come to this video sometime in the future, for instance, and you want to figure out how to do something specific that I cover in this rather long video, you can just quickly jump right to that section. Also, on a lot of my videos, there are often many comments that come out that are very similar, and instead of me answering a lot of them, what I'll do is I'll answer a bunch of them in a pinned comment. So I just ask that if you have a question and you're going to put it in a comment, just quickly check to see if there's a pinned comment that I've put where I might already have answered your question. All right, now let's get right to it. So here's my ZIF-64. I think everyone's pretty familiar with this machine. Let's just pop the cover off. This is the machine I showed last time where I had temporarily installed the RF bypass board. Well, I've installed it in a more permanent fashion now, but I'll get to that in a section. First, I want to talk about this board itself. So since posting the last video, I haven't really been able to figure out exactly where this board comes from, meaning I don't know who made it, and I can't tell you where you can buy one for yourself. Now, from a functionality standpoint, this board does work quite well, although it's not perfect. So what we're looking at here is a checkerboard pattern of white and black pixels, and I've output this through the Luma Chroma to my RetroTink 2X. But even on a CRT monitor like a Commodore 1084, it's the same thing. There is this interference rainbow pattern that is moving back and forth across these pixels. And when you look just statically at it, it's not terrible, but if you move your eyes like this across the picture, you do see this rainbow pattern. Now, I've done a little reverse engineering of this board to try to figure out what the problem is, and it turns out the way it generates composite video by combining Chroma and Luma isn't such a great design, and it's backfeeding the Luma signal into the Chroma signal. And when you're displaying a pattern that's one-by-one checkerboard like I am there, that actually creates a phantom Chroma signal. That's why we're seeing those rainbow patterns. The fix for this is actually to remove a capacitor that couples the Chroma signal to the Luma signal, and that eliminates that backfeeding. The negative aspect of this, of course, isn't the composite output is now monochrome, but it makes the S-video output look perfect. I also noticed when looking at the Chroma signal on the output of the VIC-2, some of the Luma signal is actually leaking through there as well. So 150 picofarad capacitor to ground on the base side of the Chroma signal seems to eliminate a lot of that as well. The result is a nice perfect checkerboard pattern on S-video with no rainbow patterns at all. All right, next up, let's talk about this little board that this is now mounted on. Originally, I just had this stuck right down onto the Commodore 64 main board, which was fine. It had no issues. It worked fine just like that. The only issue is it left two empty holes here at the back of the case. This is the board I have it mounted to. This is an open source project, which is a Commodore 64 RF modulator replacement. It's very similar to what's going on right here with this little yellow board, but it's larger and it's designed to be mounted right onto the motherboard. But its extra cool features are an RCA jack here and a headphone jack. This is for outputting composite video directly without a special cable, and the audio jack, of course, is for hooking up speakers without needing a cable so you can hear the audio. I had built up one of these boards, and it does work fine. If you have no RF modulator in your machine or it's totally bad, getting one of these will work for you. The picture quality is not perfect. I had some slight smearing on the output, but in the end, I don't think using one of these is really worth it because the mods I'm going to show you in a little bit with the built-in RF modulator basically do everything that this does except for the headphone output. But it did provide a nice base for this board. That way I could just solder it directly onto this board. This composite output does work properly, as does the audio output. The audio output comes in from this pin and just goes straight to here. I have jumpers now for the Luma and Chroma, so I can actually inject that directly into this board if I'm doing some testing or whatnot. It holds these two jacks in the correct spot, so they're exiting the case just well perfectly. And for my test machine specifically, I'm actually finding it very helpful to be able to take just a standard RCA jack and connect that right up to where the RF modulator RF output would be originally, just to get a quick picture. This is great for testing if I can't find my little pigtail adapters, which I use for hooking up the 64 to a monitor normally.
So a few people had pointed me towards this article, which I'd actually already seen, about improving the video quality on the Commodore 64. This person posted back in 2016 that this little fix would improve the video quality and you could do it without removing the modulator. They're referencing one of the two schematics that are floating around on the internet for the RF modulators, and they're saying that you cut this resistor here. Looking at a picture, it's actually just lifted right here, so they did do exactly what they said. But this particular mod will actually do absolutely nothing to improve the video quality of the composite or S-video output on your 64. And the reason why cutting this resistor will have no effect is pretty simple to see. It will disable the RF output, and that so much is true. But if we follow the trace back, this is the emitter of a NPN transistor. This is designed to buffer the Luma signal for the RF modulator portion itself. The composite and Luma output is fed off its own dedicated NPN transistor. These two diodes isolate these two transistors from each other, so anything that happens on this lower transistor on this RF stage is completely separate from this upper part, which is what's generating the chroma and the Luma. It's funny looking at the comments here. This one guy says it improves the picture very little, just a little more clean. Well, I'm sorry, that's not even possible. Those two video outputs are totally separated. Cutting that resistor will not have an effect. So the real reason for me to remove the RF modulator and install this buffer board on this revision of motherboard was to figure out if indeed all of the blurry problems were due to the RF modulator itself and nothing on the motherboard that we need to fix. And as you saw in part one, definitely it's the RF modulator that's causing the blurriness and no other component of the machine. Okay, I've waffled on long enough about this. This is an original 25407 Commodore 64 unmodified, and when I first set out on this project, I wanted to be able to take a board like this and with very simple tools, which means anyone can do it, modify the RF modulator to produce video output that was as good as any of those replacement PCBs for the RF modulator, like the one I have on my other machine, and I feel I was successful in that endeavor. Now, before we do the mods, I need to talk about first the different revisions of RF modulators that you'll find on different Commodore 64s. So I created a little matrix in Google Sheets, and I have columns for longboard or shortboard, the board assembly number itself, and then the RF modulator that's installed in the board. Now you'll notice I have columns for NTSC and PAL, and that's because with the same revision motherboard, like 25407, which is the one I was just showing, there's a different modulator on it depending on PAL or NTSC. It's possible there are others for different regions of the world as well. Like maybe in Japan, there's a different NTSC one than this. If you take a look at the edge of the RF modulator, there is a model number sticker on here, or there should be. So you'll be able to tell based on this matrix if the modulator that I'm showing you how to mod is the same as the one that's on your board. Now I've color-coded the different modulator types. The yellow ones here are very blurry, and these are found on the 25407s and on the KU boards, which as far as I understand are only available in the PAL regions. I'm not going to be talking about the original revision of motherboard, the one that has 5-pin video only. And then on the later long boards, the NTSC ones have this MD6-VA3405. I have these motherboards with these RF modulators here, so I can make the mods to it to improve the video quality and make sure that that validly works. But I don't have any PAL boards, so I'm actually not even sure if this is the right part number on there. I just assumed because the NTSC one is 3403 to 3405 that they follow that same convention, 3603 to 3605. Can you please let me know in the comments section if this is wrong? And until I get my hands on one of these PAL modulators, I won't know for sure if there's any issues. But down below here, you'll see I broke down the actual issues with the modulators that I know about. So the PAL MD6-UE3603, it has blurry Luma and composite video output. The color output though is fine, so the only mods we have to make are to improve the blurry Luma and composite. On the NTSC version of the modulator, the 3403, it has the same blurry composite and Luma as the PAL version, but it adds an extra bit of color smearing, but luckily we can fix both of those on the NTSC one. Moving on to the VA3405, this is the NTSC one found on these later longboard revisions. It has very sharp Luma video that doesn't require any fixing, but it has the same color smearing issues as the
NTSC version of the modulator right here, and luckily it is fixable. With the PAL one, since I don't have it, I'm going to assume that it's similar to the difference between the two NTSC modulators, which will likely mean that it has very sharp video output and it doesn't require any fixing at all. Now for short boards, it's out of the scope of this video, but I will say one thing. I own one short board and it's actually a PAL board, but I've converted it to NTSC. So it has the PAL modulator on it and actually outputs perfectly nice looking video with no issues that I can tell. So I don't think really any fixes are required for any of the short boards. To recap, I'm going to be showing you how to fix these modulators here in yellow and also fix these ones in green. This is one of the modulators off the 250-407 boards, and as you can see, it looks a little bit more complicated than the modulator that's on these later revision long boards. Now, from a complexity standpoint, they're actually the same. It's just that the older modulator only has traces on the bottom, while the newer modulator has actually removed most of the components from the top side and made them surface mount on the bottom. My goal in figuring out the mods to do to these modulators was such that I wanted a novice to be able to do the mods themselves with simple hand tools and without needing to desolder these from the main boards due to the difficulty of doing that without special desoldering tools. So really, the next step to figure out what's causing the blurriness in this modulator is to understand how the modulator works. Normally, you would just take a look at the schematics to figure out how the circuit is designed and what might be the problem. But unfortunately, there does not seem to be any published schematics for the NTSC modulator on these revisions of motherboards. There are two schematics for RF modulators floating around on the internet right now. One of them is for the PAL version of this exact modulator, although one of the issues with it is it's such a low quality scan that it's impossible to read the component values to really know what's going on. The other schematic I found was for this RF modulator right here, the NTSC version that comes on the later long boards. And I've printed out the little relevant section right here that has to do with the inputs from the VIC-2 and the outputs to the DIN connector on the machine. And the reason why I know this is for NTSC is because this has an inductor right here on the color input, which is that inductor right there. That is not going to be used on the PAL version of the modulator. So that's how I know that this schematic is specific to the NTSC version. So what I went ahead and did is I created schematics of the relevant video in-out sections for both the NTSC and the PAL RF modulators for this 250-407 motherboard. That allows me to fully understand how this modulator works and what I need to mod to fix the video quality issues. First, let's start on the NTSC version, that's VA3403. The Luma input comes in from the VIC-2 and immediately splits. It goes through two diodes which isolate these two stages from each other. The first top section is essentially a dedicated NPN transistor that goes to the Luma output on the DIN connector. Let's go through exactly what's happening. So the diode allows the signal to come through. It hits this junction here.
The reason for the resistor above the NPN transistor is the base has to be a higher voltage than the emitter, so this brings down some voltage from VCC to allow that.
Then there is a capacitor that goes to ground. And when you have a capacitor like this to ground, that's actually creating a low-pass filter. That means that it's allowing lower frequencies through and filtering out the high frequencies. This goes to the base on the transistor, which is basically turning off and on the transistor, allowing this VCC to kind of flow through. And then it's coming out of the emitter, which is pin 3, and it goes through a voltage divider there, and it outputs the connector. So the only possible thing on this entire stage that is filtering is this capacitor. So I wrote, to improve the Luma sharpness, you cut C1. Now on the NTSC modulators, there's a separate diode and transistor that is specifically for the composite and the RF circuitry. Now I didn't reverse engineer the RF circuitry because I didn't care about it. I thought it was irrelevant in this situation. But essentially, you notice this looks the same up until this point here. And what's happening is this also has a capacitor. I've labeled it C2, and that's also filtering the high frequency signals out of the composite. So I wrote here, to improve composite sharpness, cut here. It comes out of the emitter of the transistor, goes through an inductor. There is another capacitor to ground, which might possibly be filtering the signal. There's two different voltage dividers here as the signal splits. One of them goes to the RF circuitry. R14 is that resistor that guy cut in that other post I talked about earlier. And on the composite, it just goes straight out the composite.
Now you'll see a couple wires coming from down below, and what this is this is the chroma circuit, and this is how it feeds the chroma and mixes it in with the composite video. Because remember, composite is the chroma and the luma mixed together. That's what's happening here with these two capacitors. And this is happening separately with the RF and the composite. Now, it is possible, theoretically, that if you cut this R14 resistor to the RF circuitry on the NTSC version of the RF modulator, that it might somehow improve the video quality. But I actually did that as a test, and it has no effect whatsoever. R14 is a very high value resistor, as the RF circuitry requires very low current of a video signal. This is compared to composite, that when you plug in a monitor, there's a 75 ohm load on this connection, which is very significant compared to this barely any load up on the RF side. So cutting this has basically no effect. But back to these two capacitors on the composite line, I found cutting C2 does improve the sharpness of the composite. Although if you don't care about touching the composite and you only want to improve the sharpness on the luma, which is the S-video connection, you only need to cut C1. Down here on the chroma section, there's a little bit more going on because it's a little bit more of a complicated filter that's happening. This inductor, though, is what I found to cause the color smearing. I will show you what that looks like in a second, and it's very minor. But if you do remove this, it seems to have no ill effects whatsoever, except for removing the color smearing. So I'm not quite sure why it was put there in the first place. Perhaps someone who's an analog video expert could let me know. But I definitely found that removing this inductor or jumping it, just which takes it out of circuit, eliminates the color smearing. There is a capacitor to ground that's C4, and it looks similar to the one that's going to the base on the luma up above. But I did find that if you cut this, it has some ill effects of actually creating that rainbow noise effect that I showed you earlier in this video on that little orange bypass board. It lacks this capacitor, which results in that rainbow interference pattern. If you cut this on the stock RF modulator, that interference pattern is seen as well. So really on the color stage of the NTSC one, the only thing you want to do is jump out this inductor for maximum video quality. There's one more thing that needs to be done on the NTSC one, and it has to do with the power supply that's inside the modulator. It uses a simple Zener diode to create a power supply, but unfortunately, this does not have any capacitors added to it, which is a bad design practice. And looking on the oscilloscope, I could see that the power rail was quite noisy, which actually resulted in a good amount of noise in the video signal as well, the luma signal specifically. Zener diodes, when they're used in this configuration, should have some capacitance added to them in parallel to ground, and that's not done at all on this. So I found that adding 100 nanofarad directly on top of the Zener, and you can do this from the top of the board, cleans up the power supply dramatically. Okay, let's start with this very stock and unmodified 25407 main board. What you're going to need at the minimum to do this mod are some cutters like this. These are very cheap clones of these from China. You can buy these in multi-packs from Amazon or eBay or wherever. You need something that has a nice sharp tip that you can get in there between the small components and clip legs. If you want to remove the color smearing, you're going to need a soldering iron because we're going to need to jump over the inductor. And I'll use this little piece of wire here, which I've already pre-bent, to do the inductor jump. There's a final mod which I didn't mention, and that is connecting the composite output of the modulator directly to the RCA jack that's on here. So that disables the RF, obviously, and allows us to plug a video cable into it, just like I showed you on my ZIF board. And to accomplish that, you're going to need a little section of wire. I mean, I have this piece here, which is a shielded piece. It doesn't need to be a wire like this. It can be something as simple as this bodge wire. As long as it can make its way from over here to over here, it's good enough. Okay, before we get started with the mods, let's take a look at the color bleed and the sharpness. And just like we saw in part 1, the text is very blurry, especially between the risers like on the M there and the E, but also the color bleed, which is really apparent along the edge here. Now, when you sharpen the video quality by cutting the filter resistors, it actually makes the color bleed more visible because the luma is now much sharper. To really illustrate the color bleed and the fix, first we'll sharpen the video so you can see the color bleed a little better, and then we'll fix that, and you'll see the big improvement that you get from that mod. So we have two capacitors to cut. We have C1 and we have C2. It doesn't matter which side of the capacitor you cut it on, as long as you're isolating this trace up here from ground. So the two capacitors we're dealing with is this one right here, so the one I'm bending back and forth, and also this capacitor right here that I'm bending back and forth.
The way you disable these is up to you. You could probably reach in and just break them. I'm just going to cut one like that, so that capacitor is now separate. And I'm going to do this one like that. And just sort of bend them up so they're definitely not touching. And those two capacitors are now free and no longer filtering the signal going to the base of those two transistors. All right, let's power this on, take a quick look at how the video looks now. Would you look at that? That is a remarkable improvement in sharpness. Now for the color bleed, it's really visible right along here. You see how this reddish purple color is bleeding into the gray, and so is the brown? That shouldn't be there. And that manifests itself in other places as well. Like for instance, if you have color text over gray background, you'll see the color of the words kind of bleed over into the gray a little bit. And jumping that inductor and taking that out will remove this effect. Now, if you don't care, you could call yourself done. Cut those two capacitors and you're finished with this mod. Your thing is now sharp. Let's jump the inductor and take a look at the improvement. All right, the problematic inductor is this one right here, red, red, black. It's laying flat. There's an inductor next to it that's standing on end. It's going to be a little bit harder to see in the video. If you just cut this and remove it, you'll actually have no color signal whatsoever. So if you take it out, you do need to jump over it, put a little piece of wire there. Or theoretically, you can actually just connect a wire from one side to the other, leaving the component in place, which basically bypasses it. But I'm actually going to cut it out. I prefer it not to be in there at all. And to do that, I'm going to take my cutters, I'm going to flip them upside down, and I'm going to get in there. Make sure when you remove this that you leave some of the lead. That way you have something you can actually solder the bypass wire onto. So at this point, the leads are there, but we have no color like I mentioned. So I'm going to fire up the soldering iron, and I'm going to add a little jumper lead there. All right, I've cut a little piece of wire. I'm just going to hold it down in there, and so that's on there. And the other side. There we go. Just give it a little poke. Yep, that's a solid connection. Good, it's on there. All right, let's take a look at how the color bleed looks. And there we go. The color bleed is, for the most part, completely gone. Text is still very sharp. It looks good. Okay, we're not totally done. Remember I mentioned the Zener diode? That's right there, that little blue diode next to this transistor, which is the power generation. That needs a little capacitor. Don't be fooled by this little capacitor here. This has nothing to do with the power supply. This is used on the video input circuitry, which is this stuff over here. So I'm going to add a 100 nanofarad capacitor on top of that. First I need to tin the diode, which is going to be hard with the camera in the way. And here's a little 100 nanofarad. It says 104 on it. This is what I'm going to tack on there. Get the old tweezers to hold the part. And there we go. It's not pretty, but it is lower than this, so I can still put the lid on. So the funny thing about this mod is I can see a difference when I add this capacitor in the oscilloscope on the Luma video output on this board. It's much cleaner looking. But does that really affect the picture quality? I honestly can't say I could notice a difference. I think analog video is such a little bit of noise is just sort of hidden away in the analog nature of it. So really it's up to you if you want to add this, but if you have a 100 nanofarad cap, you might as well just add this on. It's easy and it only takes a moment. So the final mod is converting this RCA jack to be composite out, and all you have to do is cut this wire that runs to the center pin on the RCA jack, and then run a wire around the RF modulator over to down here where I'll show you in a second. That's where the video connection is input to the motherboard. I'm just going to quickly do this snip right there. This little green wire I have is a shielded wire, so the center conductor is the white one, and then it has this braided part that goes around the outside. I'm actually going to use that correctly. So first we'll solder the center wire onto this connector right there. There's a gap in the shielding right here where you can stick the wire. Okay, I turned this around so it's a little easier for you to see the connectors. We're going to be soldering on right there to this pin. This white connector has 4 pins in it. It is the pin right here that is towards the center. I was attempting to tin that pin and I melted the connector, so that's going to be inevitable. It's going to happen a little bit. All right, it's kind of ugly, but it is on there. All right, the video cable's been installed. The Zener diode's installed. I removed and jumped the inductor, and we cut these 2 capacitors. That is a complete mod done. At this point, I can even reinstall this cover on here, so you'll never even know that a mod's been done. All right, first thing to try is plug in the composite. So the S-video cable is not connected. I just have the composite through that RCA jack. And it's black and white, but that's not to worry. That is my retro tank, is because it's set for Luma Chroma. So here's the composite video through the retro tank, and it looks great. Not as sharp as the S video, of course, but looks rock solid. I don't see no interference lines, and it's a lot sharper than the composite was originally. I didn't really show you the before, but cutting that capacitor that filters the composite makes a big difference here as well. All right, let's unplug the composite, and we'll plug in the S video Luma Chroma. Still looking fantastic, so sharp, so crisp, and so nice. Now, I think some people are interested in seeing how this looks on an actual monitor. This machine has been modded. When I turn this on, it looks great. Unfortunately, it's really hard to record a CRT close up and have it look good. And this is because the shadow mask on the CRT is having a little bit of an interference pattern with the sensor inside the camera. It's just not quite lining up correctly, so things don't look great. Now, one thing to notice though about this monitor is if you look right to the left of the letters, there is a bit of what looks like color smearing. Unfortunately, this particular 1084 has that color smearing evident all the time, even though when I hook up this same 64 mainboard to the retro tank, you don't see it. Also, before I remove the inductor on the RF modulator, that color smearing is a lot worse. So I'm almost thinking that probably inside of this monitor is an inductor on the chroma line as well. Incidentally, I have the sharpness control turned all the way down on the monitor and it still looks this sharp. Obviously, if I turn it up, it can be even sharper, but now it looks a bit artificially sharpened. So yeah, this looks very, very sharp on a CRT when you do these mods. It's time for a quick test with the alternating pixels to see if we have that rainbow interference pattern. If I go to Adrian's tools, there is now a program called Test Patterns, and this is something I actually wrote myself to allow for alternating pixels between white and black, or really any two colors. And just like that, the screen is full with white and black alternating pixels, and it looks fantastic. No wavy lines, no alternating pixels, no interference patterns with the rainbow colors. Now moving on to the PAL modulator. It's very similar to the NTSC one, but it has one strange difference. What I labeled as Q4, this transistor here, is handling both the Luma and the composite video at the same time, while the RF has its own dedicated Q5 transistor here. This is why I said when you cut this resistor, as said in that article, there's absolutely no effect at all, because this whole stage is completely isolated from this stage up here. Now back on the NTSC one, like I mentioned, it might be possible that there's some effect, but there really isn't in practice. I actually tested that. But what's nice about the NTSC version is you can actually connect the composite signal and the Luma signal simultaneously, say to two different monitors, and you will not get a dimmer picture because you're not drawing down the current on these two transistors. They're separate and isolated. But on the PAL modulator, if you connect the composite video with 75 ohm termination and the Luma to another monitor, also 75 ohms, you're going to get a dimmer picture when they're both connected. And that's simply because as soon as you connect the monitor to either one of these, that draws down this circuit because the monitor itself has a resistor to ground. It's not going to damage anything. It's just going to look dark until you unplug one of the monitors. On the chroma section for the PAL modulator, it's pretty much identical to the NTSC one, except that inductor is missing. It's just not there, probably because it's not needed for the way PAL color works. And also C8, this capacitor, is to the right of this C10 capacitor on the NTSC one. Otherwise, these stages are essentially identical, and they both feed up to the RF and the composite signals using the same capacitor connections, just like on the NTSC. And then very interesting is the power stage here looks identical, except there is a capacitor in parallel to the Zener diode. It's a larger electrolytic, so it's not ideal. Why did Commodore leave this off of the NTSC one? I couldn't say. Here's my PAL C64 mainboard. This was donated by Dave in the UK back in January of 2020. I just noticed this has the 6569 R1 VIC2 chip. These are the early ones that only have the limited Luma levels. I really only thought these came on the super early C64s and that this board would have had the later revisions that didn't have that same limitation. Anyhow, let's get the cover off this RF modulator. It looks like it has a little tab here that's soldered down. That is different than on the NTSC ones. There we go. So this is the video output from my PAL 250 407 board, and
just like the NTSC ones, very soft along these letters here. I'm also seeing artifacts in the solid colors. Notice the solid blue has alternating lines of blue and darker blue. There's a phenomenon called Hanover Bars. If you check out the Wikipedia article on the subject, appears to be something to do with phase errors in the color information. Let's first correct this blurry video, and then we'll take another look at the Hanover Bars. Okay, so this modulator is an MD6-UE3603, and I have the schematics right here for it. So if you recall, there was only one issue with this one, and it's the capacitor C9 that we have to cut going to the base of this NPN transistor. The capacitor to cut is this green one here that's right between this transistor and this larger capacitor. It's this small green one. I'm trying to move it back and forth, but I can't. I'm trying to get in here to cut it with the camera in the way, but unfortunately, I just can't get a good view of it. So I'm going to need to move the camera out of the way while I cut this. Well, it was a pretty tight fit, and I had to cut through the capacitor and then cut the leg off. That was the only way I could do it. So if I need to restore this back to the way it was, I'll just have to desolder the entire RF modulator and put a new capacitor on. So let my experimentation help you out if you have one of these RF modulators. Well, let's power this thing up and see how it looks on the monitor. All right, there we go. Well, I'd say that there is an improvement, but I must say it's not as dramatic as it was on the NTSC machines. I'll do an A-B comparison in editing, but it's definitely sharper, but it's not as good as the NTSC's turned out. Okay, I have a test pattern up on the 64, and it has various bandwidths here, including 4 megahertz. This is basically alternating white and black pixels as close together as possible. And I hooked up the oscilloscope to the Luma output of the RF modulator, but also the Luma output right from the VIC-2, and I figured out why the picture is so soft. Here's a single shot of the Luma signal coming from the VIC-2 chip. You can see why it's so soft. The rise time and the fall time is very slow. Therefore, there isn't a lot of time spent at the top. So theoretically, it should go up, then it should go through the duration of the pixel and then drop down to black and should be alternating. And that would explain why it's so soft. And this is coming directly from the VIC-2 chip and not from the RF modulator. When I check after the buffers in the RF modulator, it basically looks very similar to this. So if this is not good and clean, then the output of the RF modulator is also not going to be that great. So unfortunately, there's no way to fix this particular problem. And running the same test on an NTSC VIC-2 chip results in a much more squared waveform, which means there's more inherent sharpness in the signal.
It turns out the issue is either with my particular VIC-2 chip or all of these R1s. I found another PAL VIC-2 chip and I stuck it in this machine, and as you can see from this picture, it is far, far sharper and looks as good as the NTSC ones. Other than some minor color fringing and of course those Hanover bars which are still visible, it looks great.
As far as the mod to output composite through the RCA jack, it's actually no different than on the other one. You just run a cable from this pin right here all the way to here. You just cut this RF connection and you can reuse this RCA jack for composite.
And finally, we have the NTSC modulator that's used on the later revisions of longboards. This is the actual Commodore schematic that I was able to take. Like I said before, it has the inductor here on the chroma signal, which means it's for NTSC color. I don't have the schematics or even a modulator to reverse for the PAL boards, so I couldn't tell you what needs to be done there, but I have a feeling based on the rest of this, there's probably nothing that needs to be done on the PAL modulator whatsoever. The design of the Luma input section here is a little bit more like the PAL modulator on the earlier one. There's only a single transistor here that handles both luminance and composite, so the same problem applies that if you plug a monitor into both of these simultaneously, it will create a darker signal. But if you notice here on the base of Q2 transistor, what's missing on this? There is no capacitor down to ground, which means there is no low-pass filtering happening on this modulator. This right here explains exactly why this modulator has a sharp video output, while the other modulator has a blurry output. The chroma stage is basically exactly the same as on the earlier modulator, and just like the NTSC one, it has the same 22 microhenry inductor here. And I wrote remove and cut or remove and jump L1. And this will have the same effect of removing the color smearing, which this modulator absolutely has. I always really liked this version of the Commodore 64 motherboard because the output looks so sharp. As explained down here, there's no filter going on. but I didn't like the color smearing and the delay that was on the color line, which is coming from this L1 inductor. So I'm glad to have figured out that it's a simple thing just to jump over that on this, and it completely eliminates that color smearing. So for modifying the 3405 modulator, there's not much to it. This is the inductor that you're going to be taking out, red, red, black. All you need to do is cut this and jump it. And now it's jumped. I just installed a short piece of wire there. I did test by actually installing a piece of wire over the inductor in place, and that seems to work equally as well. So you can honestly do either one of those. I also went ahead and used a bodge wire to go from the composite pin that goes to the motherboard there to the RCA jack, and that gives me RCA out on this modulator. All right, back to the Hanover Bars discussion. So you can see them there in the purple and the red. They're basically showing up in all the colors. I don't really see it in the yellow. Now, initially, when I first got a PAL 64 and started playing with things in PAL signal, and I saw these bars that were rather ugly, I didn't really know what was going on. So I started doing the research. And there doesn't seem to be a lot of information out there other than the fact that very old monitors and TV sets exhibit this problem, but also some very high-end professional monitors have this problem as well. And my RetroTink 2X, which is what I'm connected to right now, clearly exhibits this issue. In my reading, the way around this particular problem, and the reason why most people in PAL regions have probably never even seen these bars, is that most TVs and displays have what's called a delay line inside. And what it does is it averages the color information between two lines so that any difference in color from the Hanover bars will be wiped out because of that averaging. But of course, there's an undesirable side effect. And what happens is it halves the number of lines of chroma you have. And while that makes solid colors appear perfectly solid and not with these lines any longer, it will reduce the resolution. And I have a particular test to demonstrate that exact problem. Here's a very cool program for the 64 called Playing with Colors. And what it's doing is it's generating some additional new colors by alternating on every other line from the 16 colors that are available on the 64. Well, down on the bottom row are the solid colors on the 64 itself, and sure enough, I see these Hanover bars. But if we take this square, for example, it looks like it's made up of dark gray, which is this square, and this lighter blue, and you end up with this sort of shade. But of course, we're clearly seeing these different lines that make up this color because the RetroTink is not averaging this color information. But I have this box, which is a SCART to HDMI converter I got from China, and I know it will eliminate the Hanover bars by averaging the color information, but of course at the cost of the vertical chroma resolution. Let's test this out. And there we have it. There are no Hanover bars. These boxes down here are perfectly solid. We have no alternating lines. But look up here, remember this box we were talking about? It's made up of dark gray and this light blue color mixed together, but it looks like a solid dark blue. In fact, all of these squares here look completely solid. And that's, again, because of the averaging of the chroma information. That resolution is lost. That definition is gone. So yes, definitely NTSC has trade-offs, but as you see by this, PAL has some trade-offs as well. I tried to show playing with colors too on an NTSC machine, and this is what you get. It does not work. Well, that's going to be it for this video. I know I covered a ton of content, but hopefully you were able to follow and find it useful. If you modify your Commodore 64 RF modulator, I'd love to hear about it in the comment section below. Let me know how it works out for you. And then, of course, if you like this video, I'd appreciate a thumbs up. If you didn't, you can hit that thumbs down button. Subscribe for more videos. There'll be lots more in the future. Put any other comments and suggestions down in the comment section below. And thank you very much for watching. Stay healthy, stay safe, and we'll see you next time.